Hello and welcome back to Unit 10. In Part 3 of Unit 10, we're going to introduce the concept of center of mass. So what is center of mass? It is the point in an object, or possibly outside the object, depending on how it's oriented, representing the mean position of the object. So here I have a picture of a hammer and a picture of a wrench. The wrench is sliding across a surface, and you can see that while it is rotating, if you track the center of mass, which is these white dots, that follows a straight line. So a very complex motion is reduced down to a straight line. Same thing with the hammer. The hammer is spinning as it goes through the air. Somebody tossed it, it's like a projectile. And if I followed, say, the head of the hammer, it's doing all sorts of crazy things. But if I follow the center of mass, I get a clear parabolic arc, as I would if I considered it just a point undergoing 2D projectile motion. So how do you calculate, how do you determine the center of mass? To determine the center of mass of the object, you have to first look at what you're dealing with. Are you dealing with a system of objects where maybe you have, say, 3 gumdrops connected by toothpicks? In this case, to calculate the center of mass, it is a weighted average. A weighted average. What does that mean? It means that I sum up the position of each object multiplied by the mass of each object, and then in order to, well, one, to make the units correct, but also to eliminate the mass effect, if you will, I want to divide by the total mass, where the total mass is literally just the sum of all of those masses. Okay. As I said, it's a weighted average. So a larger mass that is located at a smaller distance will contribute differently than a larger mass that's contributed or positioned at a further distance away from your origin. Okay. But we don't always deal with a system of objects. We could be dealing with a continuous object. I don't know, maybe it's a hammer, maybe it's a wrench, maybe it's a blob. Well, as you learned in calculus, summations in calculus become integrals when you move to continuous. So the center of mass becomes the integral of the position multiplied by a little chunk of mass in there. So basically what we're saying is you're going to look at little itty bitty chunks of mass and integrate over them and add them up, right? And just as we did before, we need the total mass, which will be the integral of each little chunk of mass. Now this seems potentially very complicated and possibly, daunting. I mean, who wants to integrate over a dm? It's not as bad as it looks. In the next part, we're going to do a bunch of examples where we calculate the center of mass. We will do one where we have a system of objects, and 2 where we have continuous objects, and you'll see that it's not as bad as you might think. Meanwhile, for this unit, or this part of this unit, I guess I should say, these things can move. So let's look at the motion of a system of objects. So I can look at the center of mass velocity, which will be 1 over the total mass. Very similar to how I did the weighted average for the positions. I can do a weighted average for the velocities. Just add them all up. The other thing I can think about is the acceleration of the center of mass. And I do the exact same thing here. And if we're not dealing with a system of objects but a continuous object, then I again have to integrate. Oh, there's no summation index here. And you could do this we're not going to be working with these integrals so much. Instead, what we're going to be doing is we're going to be thinking about the motion of the center of mass based on how the position of the center of mass is changing. So just as we learned back in Unit 2, I think, I can define the velocity as the derivative with respect to time of the position. And I can think about the acceleration as the derivative, I am not writing correctly, the derivative with respect to time of the velocity. So if I know how the position is changing, I can easily, by taking a couple of derivatives, find the velocity of the center of mass and the acceleration of the center of mass. We can also think about the momentum of the center of mass. And as you might expect, the momentum of the center of mass is the total mass multiplied by the velocity of the center of mass. And if we plug in that the velocity of the center of mass is 1 over the total mass times, oh my goodness, the summation of each of the individual little velocity pieces, we see that the momentum of the center of mass is just the sum of all the individual little momentum pieces. We can also think about the force on the center of mass. We learned last unit that force was the derivative with respect to time of the momentum. And then I'm going to plug in that the momentum is mass times the velocity of the center of mass. And I'm going to make the assumption that the mass isn't changing. So I'm going to pull it out of the derivative, leaving me only the time derivative of the velocity. So I find that the force on the center of mass is the total mass multiplied by the acceleration of the center of the mass, which is what you'd expect given Newton's second law.